Now let's discuss about some Taylor series that we can get from other Taylor series. So some examples of Maclaurin series that we're going to have are given by this table here. So we have things like the geometric series that gives me that 1 over 1 minus x is equals to the series for an n equals 0 to infinity of x to the n. I have that the series of e to the x is x to the n over n factorial, like we saw last time. And we also saw last time that cosine of x can be seen as the series for an n equals 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial. In case of sine of x, you're going to get a similar result, where you're going to get that instead of the even term now, you're going to get the odd terms. And so sine of x can be represented as the series for an n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And we also saw in the past that we can get the series of our tangent. And is this particular polynomial series from n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1. Similarly with things that come from the geometric, like log of 1 plus x. And we also saw the example of 1 plus x to the k, which is the binomial series. Now, if you have that any of this Taylor power series can be used to represent a function, we can still manipulate this to obtain other functions. So for example, let's take a look at finding out the Maclaurin series for the following functions. So we're going to start with f of x being x equals cosine of x. The first thing is that you can think of this as x times g of x. And where g of x, which is cosine of x, can be seen as the series for an n equals 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial, according to what we just got in the previous one. So if you have something like x cosine of x, then the only thing that you need to do extra here is just multiply by this x that is you have over here. So this is going to be x series of n equals 0 to infinity minus 1 to the n, x to the 2n over 2n factorial. And the effect that this x is going to have is that it integrates in this series. So you get minus 1 to the n, and now it's going to be x to the 2n plus 1 over 2n factorial. So the change is minimal, but you're still getting a series for a completely new function. Similar thing happens in the second scenario, where if you have, let's say the series, you have the series of 1 minus x being x to the n, right? And then from there we said, oh, okay, so we can do 1 plus x being the same thing, but with minus 1 to the n, because I compose with minus 1. And then I integrate and I get the log of 1 plus x being the series of n equals 0 of minus 1 to the n, x to the n plus 1 over n plus 1. And now what happens is, and you can even rearrange this if you want to make it log from that start from n equals 1. For example, you can just change the index here and now make it so this is minus 1 k minus 1, and now this is x to the k over k. Instead of change this one to be from k. You can even manipulate the index if you want to, but notice that these two things are the same. And so if you want to obtain something like log of 1 minus 3x squared, you can even create manipulations that fit this out. Now, I probably didn't need to move from here, but if you want instead log of 1 minus 3x squared, notice that you just compose in x by 3x squared. you can compose down here. Notice that all this so far is being governed by this. Now at this point where we're trying to change x by 3x squared, then things are going to probably change. But now here we can see this as minus 1, and if I use this one here, minus 1 to the n, and I'm changing this by 3x, so this will be 3 to the n plus 1, and this will be x squared to the n plus 1. Over n plus 1, and then you can simplify terms in here. This n equals 0 to infinity, minus 1 to the n, 3 to the n plus 1, and this is x to the 2n plus 2 over n plus 1. Okay, and or if you just even doing it here in this transformation, this is probably gonna end up being from k equals 1 to infinity, minus 1 to the k minus 1, x to the 2k, 3 to the k over k. So again, it all depends on what changes you want to make. One of the things is like, because we made a composition here, so far all this was x less than 1, but now because we compose with this, we're supposed to have here that 3x squared is less than 1, and so this means that absolute value of x squared is less than 1 over 3, and so we probably want to take a square root, and x is going to be less than 1 over square root of 3. So there is a change here on the radius of convergency. If we're not only doing derivatives and we're not only doing integration, but we do composition, we've got to be careful with whatever changes can happen to the interval and radius of convergency. Since this is still a Maclaurin series at 0, the most meaningful change is that now we have a change on the radius of convergency from being 1 to being 1 over square root of 3. Okay, now moving on. Sometimes you can have information on some of the series. So for example here, we want to go on 3 with f of x equals e to the x sine of x, and notice that we have information for each of the series. E to the x is a series from n equals 1 to infinity of x to the n over n factorial, and this is just going to be a particular set of values that we can use. So for example, this is just going to be 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the 3 over 3 factorial plus 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 plus. And in the case of sine of x, this here is here n equals 0 to infinity, and this is minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And so this means that this is x minus x cubed over 3 factorial plus, and so this continue being a group of numbers that you can use in here, and that you can double check. But the thing is, it's going to be very difficult for me to just multiply series and try to get the multiplication of this with this. So instead what you can do is, if you want to do e to the x sine of x, you're really multiplying these terms and you want to see how they change when they add up. Okay, so you want to be multiplying these terms, and of course paying attention how they reflect, because you can keep track of a couple terms and how they're changing, but you cannot keep track of all of them. So for example, if you do 1 times all this, then you get x minus x cubed over 3, so on and so forth. And then you can go with the next term and start multiplying and start adding up. but then you gotta be careful how things are going to change. So for example, when you do that multiplication in there, you just multiply this. This is 1 plus x plus 1/2 x squared, right? This is 1 plus x plus 1/2 x squared, and this is 6, so 1/6 x cubed. And you want to be paying attention. This is x minus 1/6 x cubed plus 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 plus. And then when you multiply these terms, notice that this 1 over this is going to give me an x, right? But then over here, this x with this is going to give me an x squared. And then with the continuous things, you're gonna have to multiply here to get to know. So for example, this 1/2 x with this one here is gonna be 1/2 x cubed, and then with minus 1/6 x cubed, then you simplify, and then you're gonna have that this is 1/3 x cubed, adding up with this one as well. And so you gotta figure out how some of the terms are going to be relating with the multiplication. Try to multiply and try to get a lot of the terms of that multiplication, but at the end it's impossible since this is an infinite multiplication of keep track of all the terms. But in that way you can start seeing how it's going to develop and how the general multiplication of the series is going to go, so you can at least have some terms that represent the power series. Similar to this is the last example where we have tangent of x, and tangent of x gets into play here because of course you can represent tangent of x as sine over cosine. Okay, and so this is like, oh, okay, so I have x over x cubed 3 factorial plus x to the 5 factorial plus 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 plus, and then being divided by 1 minus x squared divided by 2 factorial plus x to the 4 divided by 4 factorial. And then e alternates here, so it's a minus, and then it continues. And so again, the procedure that you will go and do here is you need to do some sort of long division. You need to do the whole process of, well, I'm going to go ahead and take the long division process. I'm going to have to say, well, x minus 1/6 x cubed plus 120 x to the 5 is going to be dividing up the 1 minus 1/2 x squared plus 1 over 24 x to the 4 minus. So you're dividing this by this, and so what you do is you try to get the first couple terms that you get. So for example, the first one is going to be an x, and so when you multiply x by this, then you're going to find out that this is x minus 1/2 x cubed, multiplying this here, plus 1 over 24 x to the 5, and then minus and continue. And then this is now going to give me a different thing when I subtract things. This will give me 1/3 x cubed minus 1 over 30 x to the 5 plus, and so it continues, gets me this, and so now I go with the next term, 1/3 x cubed here, to go ahead and continue my long division. And if I continue my long division here, this is going to be 1/3 x cubed minus 1/6 This is 1/6 x to the 5. And then plus, 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 plus. And I just do a couple terms, but I try to keep track of the terms that I need to get to the next one. And if I subtract this to here, then I'm going to get 12 over 15 x to the 5 plus, 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 plus. And so I'm going to need here a plus 12 over 15 x to the 5 to be able to multiply this and get something here. But what this is saying is, now look, this quotient that between these two polynomials is telling me that tangent of x in representation of power series is really going to be this arrangement that I have over here. So x plus 1/3 x to the 3 plus 2 over 15 x to the 5 plus, and so on and so forth. So even if it's not very clean, because this is not a very clean calculation, you can certainly use power series from previous information from, like, for example, this table that we have over here, to just find power series for other type of functions.